Welcome back. Last time we derived the distribution for the interarrival time t, something as ft(t) that is given by lambda exponential minus lambda t. That's the distribution of the interarrival time, the PDF of the interarrival time, and is basically something like that. Of this shape here. This actually is kind of exponential decay, therefore it's known as an exponential distribution. And we can find the average and variance of the interarrival time. Basically, we can just find the expectation of the time. Interarrival time will be just equal to the integral of tft t dt. If we kind of do the integral here, 0 to infinity, t lambda e minus lambda t dt, you will find that this will be actually just equal to 1 over lambda. And we can find the variance of the interarrival time that will be equal to the expectation t minus expectation t square, and that's actually equal to expectation t square minus expectation t square. And the first term will be the integral t square ft t dt minus 1 over lambda square, and it turns out the first term will be just equal to 2 over lambda square, so minus 1 over lambda square is equal to 1 over lambda square. And actually we can find this kind of moment, this like in general expectation t to the m, let's say, just by computing the moment generation function. That's basically just the Laplace transform of like ft, that we can say define something like gs is equal to ft t e to the st dt from 0 to infinity. If we, let's see, if we take the derivative of gs over s, then you see that like there's a t coming down here, and then if we set s equal to 0, then basically we will have expectation t there. Let me just kind of explain it more clearly. Let's just compute this thing. This thing is very easy to compute. It's just equal to 0 infinity lambda e minus lambda t e to the st. So I can put this together. It's basically e lambda minus st dt, and actually this would be just equal to lambda okay, see, lambda minus s, I believe. Yeah. So now let's see, if we look at, or maybe I copied, let me just write this now, like this gs here if I take the derivative of gs over s, then I will have like just from this term will be t f t t e s t dt 0 to infinity. And then like if I take s equal to 0, then this term will become 0, right? So I take s equal to 0. This will just give me the expectation of t. That's basically this term here. And so therefore like it's very easy to compute the moment just from the from this gs here, or the moment generation function here. For example, if I want to compute like not the first moment, this expectation of t, if I also want to compute the second moment, I can just take the derivative twice. So I can gs take derivative twice. That will give me t squared ft e to st dt, right? Now again, if I set this s equal to 0, this will give me expectation t squared. And as we can see here, if I take derivative once for this gs here, actually this, let's write on this side here, take derivative once for gs here is equal to lambda minus lambda minus s squared, and I have a minus sign here, so I have note this here. And then if I set s equal to 0, that's exactly equal to 1 over lambda. That's what that I skipped the kind of like the calculation previously. And like for this guy, if I take this derivative twice, so if I take one more times for this guy, I have lambda minus s cube. I have a 2 here, something like that. And again, if I set equal to 0, I have 2 over lambda square. That's again like what we kind of given previously. I written down directly without computing it really. Okay, that's just some digression from our discussion previously, that after we have this distribution here, entire arrival time distribution, we can compute basically all the statistics we want to find. Like for what we just did, like we only find the mean and the variances, and I also show like we can use the moment generation function. That's very simple, that we can find high moment, and we can even find kurtosis like or something like high statistics very easily with the moment generation function.